How does hydroelectric energy work? Hydroelectric dams convert the potential energy of stored water into kinetic energy and then into electrical energy. By controlling the flow of water, the dam spins turbines connected to generators to produce power. Water is stored. A dam blocks the natural flow of a river, creating a large reservoir of stored water. The water behind the dam has gravitational potential energy, which is converted into kinetic energy when it is released. The amount of energy available depends on both the volume of the water and the vertical drop, or head, from the reservoir to the turbine. An intake gate is opened, and gravity forces the water from the reservoir into a large pipe called a penstock. As the water flows down the penstock, the pressure and kinetic energy increase. At the end of the penstock, the high-pressure water strikes the blades of a turbine, causing it to spin rapidly. This converts the water's kinetic energy into mechanical energy. The type of turbine used can vary based on the specific dam and water flow. The turbine is connected by a shaft to a generator. As the turbine spins, it rotates a series of magnets inside the generator, which are surrounded by coils of copper wire. This process of rotating a magnetic field past copper coils induces an electric current. The low-voltage electricity from the generator is sent to transformers in a switchyard. The transformers step up the voltage, allowing the electricity to travel efficiently over long distances through high-voltage transmission lines. After passing through the turbine, the water exits the powerhouse through a channel called the tail race and flows back into the river downstream. The water is released without being chemically altered, allowing the natural water cycle to repeat. While the conventional dam is the most well-known, other types of hydroelectric facilities operate on the same basic principle: pumped storage facilities. This system uses two reservoirs at different elevations. During periods of low electricity demand, water is pumped from the lower to the upper reservoir. When demand is high, the stored water is released back into the lower reservoir through turbines to generate electricity. Run-of-the-river systems. These plants use the natural flow of a river to spin a turbine without requiring a large reservoir. The facilities divert a portion of the river through a canal or penstock, but their power output can be affected by seasonal changes in water flow. Beyond its traditional use in large-scale dams, innovations in hydropower technology are expanding its applications for more localized, efficient, and environmentally integrated uses. In the U.S., less than 3% of the country's 90,000 dams currently produce hydropower. By retrofitting existing dams with small-scale turbines, communities can generate clean energy without requiring new large-scale construction. Hydrokinetic turbines. These devices can be deployed in rivers and tidal estuaries to generate electricity from the natural water flow without needing a dam or reservoir. The Energy Fish is a German innovation that uses a fish rack design to minimize ecological impact. Micro-hydropower systems can be integrated into municipal water pipelines and irrigation canals to generate electricity. This low-impact approach offsets energy consumption for water treatment plants and supplies power to remote, off-grid communities. Researchers are developing systems that combine pumped storage hydropower with reverse osmosis desalination. This provides a dual-purpose solution that uses excess renewable energy to pump and purify seawater, producing both electricity and fresh water. Former mining sites with natural elevation differences are being converted into closed-loop pumped storage hydropower facilities. These projects avoid the environmental impact of building new dams while leveraging existing infrastructure for energy storage. Fish-friendly turbines, novel designs, such as the minimum gap runner turbine, have blunted blades and smaller gaps to allow fish to pass through facilities with a minimal risk of injury. This mitigates one of the primary ecological concerns of conventional hydropower. Advanced environmental monitoring technologies use drones and sensors to track fish movements near hydropower facilities. This provides real-time data to help operators improve the safe passage of migrating fish. Some hydropower facilities are using their reservoirs to manage and enhance water quality. For instance, solar-powered aerators can be used in reservoirs to maintain oxygen levels, which helps keep water ecosystems healthy. Underwater kites. These tethered kites fly underwater in a figure-8 pattern within tidal and ocean currents to generate electricity. This technology can produce reliable power from slow-moving currents and poses a lower risk to marine life than rotating turbines. Wave energy converters and tidal stream generators harness the consistent and predictable power of ocean currents. This technology offers a promising high-yield source of clean energy for coastal regions. Smart digital control systems use artificial intelligence and machine learning to analyze large data sets from hydropower plants. This allows operators to predict energy demand, optimize output, and conduct predictive maintenance to reduce costs and increase uptime. Creating a digital twin, or a virtual model, of a hydropower plant allows engineers to simulate its performance under different conditions. This helps optimize the design and operation of both new and existing facilities. These advancements are making hydropower more flexible, scalable, and versatile, from powering remote communities to managing water supplies. These innovations in hydropower technology are expanding its applications for more localized, efficient, and environmentally integrated uses.